Welcome to our presentation today, pushing the power density of silicon carbide modules and the outcome of overstressing these modules. My name is HelenAnn Brown, and I am the Strategic Marketing Manager for Apex Microtechnology, and I'll be your presenter today. So a quick disclaimer and introduction to our presentation. The following research was intended to showcase performance and benefits of using integrated modules compared to discrete solutions. As each module is unique, each design requires its own technical approaches. And a very big thank you to the Technical University of Madrid, UPM, for completing this independent study and providing the information for this presentation. We really appreciate our partnership and working together. So we're going to start out by giving you a little bit of information about this particular study. So what we did was comparing the silicon carbide module to discrete components, and we compared multiple items, including engineering time, PCB size comparison, switching ripple, and then we'll get into talking about overstressing the module and research that we did there as well. So the first thing we included a couple of design revisions. The first one is version 1. This was completed by an entry-level engineer, maybe a new hire right out of college, graduate level student, or a beginner engineer. The second one, version 2, is a mid to senior level engineer. So think on the professor level or an engineering fellow. In terms of expertise, this will help us throughout the study. So the first thing we talk about is engineering time. And as I mentioned, the versions, they're outlined here at the bottom. And this compares the time of soldering, PCB, schematic, using a discrete, and using a module, and you can see the hours here at the bottom. So on version 2, which is our mid to senior level engineer, you can see about a 50% reduction in engineering time using a module versus discrete. So really going to help save out on some time. The second thing that we chose to compare is a PCB size comparison. Everyone is pushing the power density and really trying to maximize the space on their board. And that's where a module can really come in shape here. So the first thing we did was outline only the active components, which are going to be the dotted lines on these two charts. And you can see here, using a module is a 67% size reduction. So really quite the space savings. And this is version 1. So version 2, again, a 60% size reduction. So a major benefit to using a module here as we're pushing power density moving forward. The next thing we'll get into is the switching ripple. So first I want to outline the test conditions. All tests were performed with the following specifications. The switching frequency, 200 kilohertz, the duty cycle, 50%, and both the rise and fall dead time are 100 nanoseconds. So here we're going to show the switching ripple. This chart shows the switching ripple at 100 volts and 3 amps. On the left side, you're going to see the discrete components, and on the right side, the module. What you see here is really related to density and shorter traces on the module. That allows us to have better performance characteristics such as reduced ringing and oscillation, which we can visually see here. Quite a significant difference. Next thing, we'll start talking about our overstress. So why is that important? We know that silicon carbide devices are known to withstand temperatures but beyond 200 C, and everyone is very interested in that. This is one of the major benefits of silicon carbide. And we know that customers' applications, systems are typically operating right at the bounds of the SOA or even outside of the SOA. We're always pushing that SOA whenever we're operating these devices. And lastly, most failures are not due to the temperature itself, but rather due to thermal stress caused by the cyclical change in temperature. So first we're going to talk about the standard operation. And this slide is really demonstrating the module operating at normal conditions, which are inside the SOA, including the junction temperature, which is spec'd at 175 C. Here we can see it operating at 128 C. And the case temperature, which is spec'd at 125 C, and we're operating here at 88 C. Now we're going to start to see a little bit of stress on the module. So the junction temperature here is targeted at 175 C. Now we're really pushing that. We're at 198 C. But this is silicon carbide, and we're still under 200 C and operating well. The module is doing great. However, we are exceeding the 50-watt power loss. And you can also see the voltage, the current, and the watts here on the left side. So now we're getting into some deep trouble with our high overstress. So we can see that the junction temperature is at 448 C. We have well surpassed that 200 C. So the module's overpassed that junction temperature. When the module reached 168 C, the bootstrap diodes reached 200 C, and the bootstrap ultimately failed. The resistor and one diode opened, the other diode is short-circuited. And a couple of operating conditions here. We're operating at 97% efficiency, and the load scheme was 5 milliseconds at 10 amps and 45 milliseconds at 6 amps. So we're going to get more into tying that load scheme on the next slide, where we're talking here about power cycles. So in the previous slide, we defined that load condition, and here we're showing the power cycles under those conditions related to the efficiency. And what we really see here is operating at low currents, the efficiency is defined and dominated by switching losses over conduction losses. And we can see some nice fireworks. And here's a visual representation of those fireworks. This is the effects of too much stress on the module. So to summarize, using a module over discrete really provides several benefits that we outlined in the presentation, including size, engineering time, and performance characteristics. Also, modules are more forgiving with regards to short-term overstress. We can push that SOA here with a module. And lastly, silicon carbide survives extreme overstress, while other components, such as the bootstrap, may fail first. So silicon carbide is really living up to that expectation. Thank you guys for listening to the presentation. If you're curious or want to learn more about APEX, please reach out to us. You can find my email on this slide or visit us at apexanalog.com. Thank you again.